The Earth is 4.6 billion years old. In this clip, we rewind through our history until we end up at the very beginning. Life is seen as an impossible event by many, a large-scale event. But it could simply have rained down upon us. The early Earth was glowing hot and was struck by many asteroids that could have contained the essentials for life. The first life forms were perhaps single strands of RNA that happened to be good at recreating itself. It is quite astounding that from such a large-scale event, such small-scale life forms could develop.
On a small scale, whenever any form of life springs into existence, whether it be a flower being pollinated by a bee, a male fish fertilizing some unattended eggs, or a sperm cell reaching an egg, the complexity of the life form from that point onward begins to increase. Imagine this. In 1993, two genetic information-rich cells met and began to multiply, probably inspired by the gene providers. And now, 21 years from then, a being composed of almost 40 trillion cells working in unity speaks about life. That's a lot of orderly work and a tremendous increase in complexity at a rapid pace. So, it may seem that growth of life forms and evolution in general violates the key thermodynamic principle of constant progression towards disorder, entropy. Nevertheless, the nutrients and the resources living organisms consume, as well as the heat and waste products that we excrete, serve as an entropic byproduct of our progression. Furthermore, entropy serves a vital role on Earth, as in the grand ecosystem it provides both space and nutrients for new life forms to grow and evolve, thus enclosing the cycle of life. Czech poet Václav Havel described this relationship between life and entropy in such words: just as the constant increase of entropy is the basic law of the universe, so is the basic law of life to be ever more highly structured and to struggle against entropy. So, in consequence, life and entropy can be seen as two sides of the same coin, as the latter is the driving force behind evolution of all life.
Everything we saw at the start of the video happened. It's actually happened. So how did it happen? Like, why does a thing, whatever it might be, suddenly change? The study of the change of internal energy in physical phenomena is called thermodynamics, and its answer is as follows. We are familiar with the concept of temperature, and perhaps to a lesser degree also with the concept of energy, but what is at the heart of these concepts? Thermodynamics has established properties that allow us to look meaningfully at this change: temperature, internal energy and heat, and entropy. Temperature can be seen as the average kinetic energy of the molecules in a material, and internal heat and energy is the change in this kinetic energy that happens when two thermal objects touch each other. Consequently, a system has a certain internal energy associated with its temperature, and this energy can move in such a way that it flows from the highest energy point to the lowest energy point. Entropy, then, captures two consequences of the zeroth and first laws of thermodynamics. The first is called the Kelvin statement, and it is as follows. An object that has a certain temperature cannot do work, that is, lose energy or produce usable energy, if no energy is allowed to leave the system as heat. The second statement, or the Clausius statement, is as follows. An object that has a certain temperature cannot lose energy as heat to an object with lesser temperature without requiring external work. Both statements are statements about spontaneous events. Given the right conditions, and the right objects, and the right amounts of time, these things will happen. This too is a consequence of the zeroth and first law of thermodynamics. These concepts are demonstrably the same concept. If the Kelvin statement is not met, then the Clausius statement is not met, and conversely. The change in entropy of a system is defined as the amount of energy that a system loses as heat divided by the temperature at which the system loses this heat. From this relation, it is deducible that the entropy always increases. What life on a small scale shows is the opposite. It seems that the entropy time plot performs this elegant sine wave where growth is followed by decay, which precedes growth, which is again followed by decay, and so forth, as seen in the sine wave we saw earlier. However, when we zoom out and see the bigger curve, it might look a little bit more grim. Entropy will increase and the universe will reach its final state in which no energy will be transported, and all will end in a dark, dark, cold oblivion. But it is not so bad, because we have life ahead of us.